In this video, we're going to look at finding the roots of polynomials when they're given their graph. And not only that, we're going to look at how to write an equation from a graph based on what its factors are. Now, the roots of a polynomial, or in the case of this video, or these first two examples, quadratic expressions, are going to be nothing more than the x-intercept. So if I'm looking on this first graph here on the bottom left, and I look and it crosses the x-axis twice. It crosses the x-axis at negative a, and it crosses the x-axis at b. Now both of those x values are considered the roots. And so if my goal was just to write the real numbered roots, it would just be x equals negative a and x equals b. Now, in this video, we're also going to talk about what the multiplicity of a root means. And if I zoom in here on this picture, notice how if I'm looking at this 0 here at x equals negative a, if the curve passes straight through that x value, so it passes straight through, kind of like a line. Now, I know in reality there's some bend there, but it behaves through there. If I zoom way in, it's locally linear. It passes straight through that point. We're going to say it has a multiplicity of 1. And the same thing happens here at x equals b. It passes straight through that x-intercept like a line does, and we're going to say that multiplicity is 1. Now, we'll build on that topic a little bit more when we're trying to write some factors. Now, let's look at this graph over here to the right-hand side and say, all right, well, not all x-intercepts or zeros of polynomials will have multiplicities that are 1. They could be multiplicities 2, multiplicities 3, or so forth. But in the context of this video, we're going to look at multiplicity 1 and multiplicity 2. At x equals c, this x-intercept here, we have a multiplicity of 2, which means that what the graph does is it behaves like a parabola around that point. It touches the x-axis, and then it comes back on the side it came from. So it touches that x value, and then it doesn't go up underneath the x-axis. It stays on the same side after that point and comes back from the side it's on. Now, it could also be below the x-axis, behave the same way, where it could touch and come back down. All right, so graphically, that's how we'll look to find the roots, which are nothing more than the x-intercepts, and to indicate what their multiplicities are. So let's look at a couple of examples here. So here we want to find, we're given the graph of some function of x. I want to know what are all the real solutions of f of x equaling 0. So our real numbered solutions here are nothing more than what the x-intercepts are. And so we're looking here at this first graph on the left-hand side. And say, all right, well, I'm looking for everywhere it touches the x-axis. Well, it touches the x-axis right there at negative 2. And so we have x equals negative 2 as a real numbered solution. And if we needed to, now it's not always the case for just writing a list, but to build on for down the road, or maybe even algebra 2, we can identify that multiplicity. That multiplicity is 2, and I'm going to abbreviate that and write mult2 because it touches and it comes back on the side it came from without passing straight through. Now, we also see a second place where it goes through the x-axis, and it goes through the x-axis at 2. So that would also be considered a solution if I was just going to list them. And what it does is it passes straight through there, so that's a multiplicity of 1, and we're not going to write multiplicity of 1. And there's one more place that it crosses the x-axis. It crosses the x-axis at 7, so I write x equals 7, and it goes straight through there. So that is also a multiplicity of 1. Well, we don't write the multiplicity of 1s, but if it's something greater than 1, like 2 or 3 or so on, we would indicate those. And here we have I'm looking at this graph, and I start working my way from left to right. And we have the first place it crosses the x-axis is at negative 6. And it passes straight through there. So that is a multiplicity of 1, and I don't write that multiplicity. I just leave it as x equals negative 6. Now, we go on to the next one. Now, you do not want to include where it crosses the y-axis. That is a very common mistake, and I don't want to include that. I'm only looking for x-intercepts here to be classified as my real number 0. So we move our way to the next one, and the next place it crosses or touches the x-axis is at x is equal to 1. And at x is equal to 1, it touches the x-axis and comes back on the side it came from, and when that happens, we say it's a multiplicity of 2. I'm going to abbreviate that and say mult 2. And we have a third place where it does it. It crosses the x-axis at 7 here. And so I'd write x equals 7 solution, and it passes straight through. Passes straight through, that means a multiplicity of 1. Okay, let's do another one here. All right, so finding all the real numbered zeros. So I'm looking for, or in this case, the roots. I'm looking for where does it touch or cross the x-axis. Well, I'm looking from left to right, and I see the first one's at x equals -4. And it passes straight through that x value. So it's a multiplicity of 1, so I'm not going to write anything else. Now we go to the next place it crosses, and it crosses right here at the origin. And a lot of people will get confused as to what to write when it crosses through the origin. That x value is at x is equal to 0. So when it passes through the origin, it's at the solution there is x equals 0, and it passes straight through like a line, so it also has a multiplicity of 1. And the last place it crosses the x-axis is at x is equal to 4, and it passes straight through there as well. So all three of those zeros have a multiplicity of 1. Okay, so now we're going to advance on that concept of knowing where a polynomial has its roots and its x-intercepts at, and use that graphical behavior to help us construct an equation for what we're looking at. And in order to do so, we're going to use the factor theorem for polynomials. Now, what the factor theorem tells us is that if x equals c is a 0, meaning it touches the x-axis at c, then we know that there will be a factor of x minus c. Likewise, if it has an x-intercept or 0 at x is equal to -c, then that means x plus c is going to be a factor. And graphically, we're going to apply this factor theorem based on the multiplicities that we talked about earlier. And so let's look here. If I have this same graph that we were looking at just a little while ago, and the graph crosses or has an x-intercept at x is equal to -a. All right, what that means is that root of -a is going to generate the factor x plus a. And the root or the x-intercept at x is equal to b here is going to produce the factor of x minus b. Now, both of those zeros have a multiplicity of 1 because the graph passes straight through there. All right, it doesn't touch and come back from the side it came on. It doesn't curve its way through, so we'd say it has a multiplicity of 1. What that means is we could set up an equation for that polynomial, or in this case, the parabola, and say that a general form of this would be the product of all of its factors. So I could create a polynomial that will have those same x-intercepts and those same characteristics around those x-intercepts by multiplying the factors together. Now let's look and say, well, what happens when we have that multiplicity of 2? So this is the same graph we looked at earlier. So the multiplicity of 2 means that the graph will touch at that x-intercept, and it will come back on the side it came from. So it doesn't actually change sides. It stays on the same side it was on. So it touches and comes back where it comes from. And we said that means multiplicity of 2. Well, in terms of the factors, what that means is if I had that x-intercept at x equals c, that means I would have a factor of x minus c. The multiplicity of 2 means that we're going to square that factor. We would raise it to the second power. So an equation for this quadratic that has a multiplicity of 2 at x equals c would be y equals x minus c squared. And so I would create a parabola that would have that same behavior on the x-axis. So now let's apply that to a couple of problems here. And so what we want to do is we want to select the answer choice that will produce a polynomial or a quadratic expression that will have the same characteristics as the one we're looking at. And what we do is we are going to start off by writing our real zeros. All right, so our roots are our zeros here. And I'm just going to work from left to right. So I have a 0 at -1. And it passes straight through. So that means it's a multiplicity of 1. So I'm not going to write anything else with that. And then we're going to go and say, all right, well, it does it again. It crosses again at 3. And it passes straight through at 3. And so those are the only two zeros that we have to work with. Now you're going to take both of those and we're going to write them into factors. So if I have this 0 at x is equal to -1, the factor becomes x plus 1. You got to change the sign. And the 0 of x equals x equals 3 produces the factor of x minus 3. And so our polynomial here that we could write would be the product of those factors. So it would be y is equal to x plus 1 times x minus 3. All right, and so I would select the answer choice that has that product. Now remember, multiplication is commutative, so it doesn't necessarily have to be in that same order. And so we get this one here. All right, so we want to write the equation in factored form, or identify the answer choice that has the factored form of the polynomial we're looking at. And so you'd start by writing out your zeros and indicate any additional multiplicities. So I have my first 0 at x is equal to 2. I look at the behavior, it passes straight through there. So it's a multiplicity of 1, and I don't write that part. It also has an x-intercept at 8. So I write x equals 8. And I go look at the behavior at 8. It stays on the same side. It makes a kind of a U. It looks like a little parabola there. It doesn't actually change size. So here's a multiplicity of 2. So now we're going to advance this. And we're going to write our factors. Well, the factor for x equals 8 is going to be x minus 8. And since it was a multiplicity of 2, that means I'm squaring that factor. And the 0 of x equals 2 means that that factor is going to be x minus 2. And our polynomial here that we would write the equation of in factored form would be y equals x minus 2 times x minus 8 quantity squared. And so I'd go look for that and say, all right, well, which one do I see? I don't see anything that has an exponent of 2, but what I do see is I see x minus 8 multiplied to itself twice. That means the same thing as the exponent of 2. And so here's our answer choice.